Hey everybody, in this lecture we're going to be talking about the origin of Earth. I'm going to introduce the topics of the creation of the universe and our solar system and the Big Bang Theory, but most of the lecture today is going to be spent on Earth characteristics and what it means when we say things like the Earth system, and most importantly, the Earth's internal structure. So we're going to talk about the formation of the solar system, and sometimes those topics are hard to talk about when they're conceptually difficult. So I'm going to direct you to watch this 6-minute YouTube video, which does a great job of explaining it.
This is the story of our Earth's formation 4.5 billion years ago, and of a little asteroid called Bennu, who's also survived until now. We have the team at NASA to thank for bringing us this video.
The Milky Way, home to billions of stars, rising and setting over billions of worlds, including our own. In this vast expanse, how did our sun, the Earth, and the planets come to be? In recent decades, our understanding of the solar system's evolution has greatly improved, but deep questions remain. To answer those questions, astronomers are preparing to visit someplace very small. Asteroid Bennu. A lump of rock and organic material, the early building blocks of the solar system, of Earth, of us. Bennu is a time capsule, and its journey takes us way, way back, 4.5 billion years. The raw ingredients of Bennu and our solar system originated in a stellar nursery, a vast cloud of hydrogen, helium, and dust. Our own sun doesn't yet exist. Nearby are hot stars like this one, quickly burning up its fuel and destroying itself in a colossal explosion called a supernova. The explosion destabilizes our cloud, causing it to collapse. In the geologic blink of an eye, 100,000 years, gravity and angular momentum flatten the cloud into a swirling disk. In the center, where molecules crash together tightest, a protostar revs up to incredible pressures and temperatures. Deep within the disk, clumps of dust not much larger than a grain of wheat are flash heated into droplets of molten rock, called chondrules. The source of this heat remains a mystery. Chondrules are destined to become the building blocks of the solar system. Coaxed by gravity and turbulence, the chondrules clump. They grow into the first asteroids, into mountains, into planets. The asteroids are rubble piles of rock, metal, ice, and organics. This large asteroid is the parent body of Bennu, a protoplanet whose size we can only guess. Closer to the protostar, a planet begins to form, and then dawn in the solar system. The protostar undergoes fusion and ignites, revealing our sun. But the solar system is far from finished. Jupiter most likely forms near its outer edge, but just 500 million years after the sun ignites, some believe that it slowly moves inward. Its massive gravity ripples the asteroid belt, disrupting countless asteroids and comets, flinging them toward the sun. They rain down on the inner planets, hammering and remelting large portions of their crust. Did these impacts also deliver organics and water, key ingredients for life? Back in the asteroid belt, Bennu's parent body is lucky. It survives this period of heavy bombardment. The solar system cools and calms. Jupiter and its many moons assume the orbits that we see today. Billions of years of quiet follow, more or less. Then 1 billion years ago, one theory suggests a collision shatters the protoplanet. some of the debris loosely coalesces into a new, smaller body, Bennu. But Bennu will not stay in place. Dull, non-reflective, it slowly migrates toward the sun. Solar heating turns its warm side into a low-intensity thruster. Through millions of years, Bennu's orbit gradually tightens until it interacts with Saturn's gravity, altering its trajectory and hurling it into the inner solar system. Close encounters with Earth and Venus follow. Their gravitational tugs may have repeatedly stretched and reformed Bennu, turning it inside out and pulling off loose material. As a result, it has no satellites of its own, until now. Today, NASA is sending a spacecraft called OSIRIS-REx to explore Bennu and retrieve a sample. Why? Bennu has survived its long journey and settled into a near-Earth orbit, bringing its secrets within our reach. Now it is ready to teach us more about the solar system's history, its formation, its evolution, and our own place among the stars.
Interesting. I think it does a really good job of explaining the Big Bang Theory and the formation of our planets, because these concepts are difficult to understand sometimes, but having those graphics can help. So the Big Bang Theory is the theory where all matter and energy, everything in the universe, was initially packed into an infinitesimally small point, which then exploded and started the formation of the universe about 13.8 billion years ago. All these atoms formed during the Big Bang, and they collected into a nebulae, which then, due to gravity, collapsed into these balls to produce energy, and those were the first stars in our galaxy. And so in the formation of the solar system, when we talk about geology, why is that important? Well, you have all of these particles and dust that's colliding and collecting. So these particles clump together, and due to angular momentum and therefore the gravitational pull that's created, it starts to create these planets. So planets formed from rings of dust and ice orbiting the stars. And so we are all formed from stardust. And when these forms were large enough, that's where we got the differentiation in planets. And especially when we talk about the Earth, we have a differentiation in densities within our planet. So we have different layers within the Earth structure itself. So why are planets round? Well, I kind of already touched on it. So once a planet is large enough, the interior becomes warm and soft enough for flow to respond to the pull of gravity. So, so when you think about having like a ball of clay, and if you're to just spin that around, you have enough centrifugal force that small protrusions on the outside will be pulled inward, and the mass is then evenly distributed around the center, so that the force of gravity can be about the same around all points of the surface. The picture here on the right is the Earth's gravitational field. And so you can see where we have different gravity anomalies. And there's some correlation there with gravity anomalies and plate tectonics. You see how we have some warmer colors here along the western edge of South America. We see some cooler colors here in the oceans. Here's the Atlantic Ocean. So we're going to touch more about Earth's gravitational field in a future lecture. Okay, so when we talk about Earth systems, we have a few interactions between these systems that are happening all the time. So we have the atmosphere, the hydrosphere and cryosphere, the geosphere, and the biosphere. So let's talk about each of these individually. The atmosphere. So at approximately 10,000 kilometers above the Earth's surface, there is an increase in the density of gas. And this marks the edge of the Earth's atmosphere. We use the unit measurement of atmosphere, abbreviated ATM, so you might see that and the average air pressure at sea level. So 1 atmosphere is about 14.7 pounds per square inch. Okay, the hydrosphere. When we talk about the hydrosphere, we're talking about the Earth is covered mostly in water. So about 70% of the Earth's surface is covered in water, and that therefore there about 30% is covered in land. And about 98% of our water is in the ocean. And the rest of the 2%, those minor accumulations occur in fresh water, like in lakes or streams and swamps. And there's a larger amount of water that exists underground, which we call groundwater. And groundwater is where water fills tiny holes and cracks underneath the surface. And this is typically where we get our drinking water from. Groundwater is typically our main water source. And we're going to have a whole lecture on all these different water sources and talking about lakes and rivers and oceans and groundwater. So where do you think the water comes from Ventura County? Well, let's go ahead and search for it and see what we find up. Okay, so here's a website that shows the water quality report for 2018. So let's see if we can find some information here about where our water comes from. This is for Ventura County. So if we go to the second page here, okay, where does the district's water come from? It says that 81% of our total water supply comes from the State Water Project, and the state water originates in Northern California, where it's captured in reservoirs north of Sacramento, and then released into the delta of the Sacramento and San Joaquin rivers. It's then transported via the 444-mile California aqueduct to State Water Project contracts in Southern California. So you may have seen this aqueduct if you're driving north from Ventura County or LA, and you might see it along Highway 5. Let's check it out. Okay, so I'm going to hit pause. Okay, so here's a map that's showing that watershed. So here we can see that the California Aqueduct, which is this brown line, you can follow it all the way north to the San Joaquin River and see in Northern California where we get most of our water, and it comes down this aqueduct. So let's look at it in Google Earth. Okay. So if you haven't used Google Earth before, I'm going to be using this a lot throughout the semester because I think it's very interesting and a cool way to look at geology. Okay, so let's see if we can locate the aqueduct. And let's just zoom in until we can maybe see its character. Oh, here it is. You see it now? This is the aqueduct. And well, it's trying to load here. It may be difficult to see, but once you see it, you can't really unsee it. So let's go north and see if we can follow it. Okay, so here it's reached a large body of water. And you can see that actually the aqueduct continues to go further north than that. But what I want to do is let's follow it down south. So here we are. Okay, we're pretty far north now. Here's like Monterey area. Here's the bay. So you can see that the aqueduct does go much further north than that. But let's follow it south and see how close we can get it to where we are in Ventura County. Okay, let's cruise through here. The aqueduct does seem to parallel Highway 5 for a lot of its journey. You can see how it cross-cuts some of this agriculture here within the San Joaquin Valley. So let's keep going south. Can you still see it? Here it is. Keep cruising south. Here we go. Now if I zoom out further, can you still see the aqueduct? Maybe because I've been looking at it. But here it is still. Here we go. And now we can keep going south and further south and further south. It's cutting a little bit to the east here. And it seems to stop right here, just right over where the Grapevine is, Highway 5. And let's see if we can try and trace it on the other side. So it comes out down here, just on the other side of this ridge, and then it splits. So you can see that part of the aqueduct goes to the east and part of the aqueduct goes to the west. So now if I turn on roads, now this might help you figure out where we are. So you can see the aqueduct cuts down through here, follows these bodies of water further south, and this is Highway 5, and here's 126. And so if I zoom out a little bit further, you can see that we're down here in Ventura County. So all of that water from Northern California does go down that long path of the aqueduct all the way down to where we are here in Ventura County. Okay, next is the Cryosphere, which is the frozen portion of the Earth's hydrosphere. And in polar regions and at high elevations where we have lower temperatures, water occurs in solid form as ice. This is where we see glaciers or thick sheets of ice that's built up in streams. Ice also forms a relatively thin sheet over the surface of the ocean in the polar regions and near surface groundwater, which is called permafrost. We see that often in places like Alaska, where there's significant freezing year round. Okay, next is the geosphere. And the geosphere is the solid Earth from the surface to the center. So the surface of the geosphere is not smooth by any means, and we classify these changes in how smooth or how rigid they are, and that's called topography. We call topography the changes on top of the surface of the Earth, and then in the subsurface we call that bathymetry. So bathymetry is the small variations of the seafloor, so underwater. So if we look at the topography here of the Grand Canyon, can you try to visualize what the Grand Canyon looks like? Maybe some of you have been there. And so this topography map is quite impressive because the Grand Canyon is very variable in the differences in elevation over space. So let's look at it in Google Earth. Okay, so here we are at the Grand Canyon. If we have a zoomed out view, you can see where the river has run through here. And if we get a little bit closer in Google Earth, you can really see the variations in topography, the variations of elevation, and you see how rigid these edges are of the Grand Canyon. So we represent that in lines on a map, and each line represents a difference in elevation. And we're going to be talking more about topography throughout the semester. The geosphere is composed of Earth materials. And when we say Earth materials, we mean everything from the organic chemicals and rocks and minerals and sediments and grains that are found on Earth. And we're going to be talking about those more at length throughout the semester, especially minerals, which are the natural substances that most everything is made of. And we're going to go into great detail about all the different types of rocks, igneous, sedimentary, and metamorphic. And later on this semester, we'll talk about metals and how they're formed and how we collect them and how we mine them. So all of these things are part of the geosphere, and the geosphere is composed of Earth materials. Okay, the biosphere is an aggregate of all living organisms. And the biosphere encompasses regions of the Earth's surface as well as a few kilometers below the Earth's surface. So when we talk about living organisms like trees, for example, they could have really deep roots that go below the Earth's surface. So an aggregate of living organisms would be us. So here's a map of the human population. It's in density. So you can see here in North America that we're pretty dense, but not nearly as dense as Europe and India and Asia. So the pink and red colors mean that it's more dense. So you can see how North America is not nearly as densely populated as other parts of the world. And this is an example of the biosphere. Okay, let's talk about the Earth's interior. So the interior of the Earth is composed of denser material than the outermost layer, which means that density increases with depth. The greatest mass exists at the center. If this were not the case, a centrifugal force due to the spin of the Earth on its axis would pull the equator, causing the shape of the Earth to be more like a disk than to be completely round like it is. So because the greatest mass is at the center, that's why the Earth is shaped so spherically. Okay, so pressure increases with depth. About 1,500 feet below the surface is about 300 atmospheres of pressure. Remember that ATM stands for atmosphere. So at the center of the Earth, pressures are estimated to be 3.6 million atmospheres. That can be kind of tough to conceptualize. So just think about when you're at the side of the pool and you jump into the pool and you swim to the bottom, maybe 10 feet underwater, and you feel the pressure changing in your ears. That's a little bit over 1 atmosphere. So if you think about what 3.6 million atmospheres is, that's a lot of pressure. Temperature also increases with depth. So at the surface, let's have a nice comfortable 70 degrees Fahrenheit. 20 miles below the surface, temperatures are 1,200 degrees Fahrenheit. At the mantle core boundary, temperatures reach 6,000 degrees Fahrenheit. And we have no way of measuring the temperature of the Earth's core, but calculations estimate it to exceed 8,500 degrees Fahrenheit. It's really hot. Okay, let's talk about the Earth's layers. We're going to look at each one of these individually. So we have the core, we have inner and outer core. We have the lower and upper mantle, the asthenosphere, the lithosphere, and then the crust. Okay, so the core is separated into two. We have the inner core and the outer core, and the boundary between the two occurs at about 5,100 kilometers. The inner core is solid, and it's composed of iron alloy, and the outer core is partially liquid. And that's because the temperature is so high that the iron alloy flow is what generates the Earth's magnetic field. So we have the inner core, which is solid, the outer core, which is partially liquid but still quite solid because of the extreme pressures and increase in density as you get closer to the center of the Earth. Above the core is the mantle. So we have the lower mantle and the upper mantle. So the mantle is about 2,800 kilometers thick. And this consists mostly of ultramafic rock called peridotite. And even though it makes up most of the mantle and is the most abundant rock in our planet, we don't really see it too much at the surface because it's difficult for rocks from the mantle to reach all the way to the crust. So the mantle is divided into two. We have the lower and upper, and the boundary between it occurs about 660 kilometers. So the mantle is mostly solid. However, at around 100 kilometers, it's soft like wax and can change shape over time. And this is called plasticity. So the mantle is impacted by convection. And that's where a slow creeping motion of the Earth's mantle caused by convection currents carries heat from the interior of the planet's surface, carries heat from the interior to the planet's surface, excuse me. So warmer rock rises while cooler rocks sink. So think of this like a lava lamp. So you have hot mantle that rises to the surface, and as it cools, it can come down as a slab. So we see this in around the Earth here. So we have a plume of warm mantle rock that rises, and it's formed at a mid-ocean ridge. And where we see the cooling occur is where we have a subduction zone where part of the plate is pushed beneath the crust and cools, and we call that a slab. So at some of these weak zones, the mantle may ooze to the crust. And so we're going to talk about plumes, mid-ocean ridges, and that sort of thing when we talk about plate tectonics. Okay, above the mantle is the asthenosphere. And the asthenosphere is technically a portion of the mantle in which rock is plastic and can flow. So the asthenosphere is made up entirely of a section of the mantle that generally lies around 100 kilometers, and the base of this is known as the transition zone. Above that is the lithosphere. And the lithosphere is the outer layer of the Earth that consists of the crust, plus a relatively cool uppermost part of the upper mantle. The lithosphere is rigid, which can bend or break, but does not flow. And on top of that is the crust. And the crust is the outermost layer of the Earth. At the base of the crust is what we call the moho. And the crust is relatively thin compared to the rest of the Earth. It's about 0.1 to 1% of the Earth's radius. And the crust can be split into two categories, the oceanic crust and continental crust. And we're going to be looking at that much more in the next lecture when we talk about plate tectonics. So what did we learn? We learned that the Earth is a planet. We first looked at a YouTube video about the Big Bang Theory and the formation of our planet. The Earth is old, very old. We have rock evidence that shows that the Earth is about 4.6 billion years old. The Earth is spherical in shape. We talked about how density of the Earth helps create the gravitational pull, and therefore the Earth rotates with centrifugal force, and that's why it's spherical in shape. The Earth has complex systems that interact with each other. We looked briefly about the hydrosphere and where water comes from in Ventura County. We talked about the cryosphere and briefly about glaciers, but we'll have another lecture on that. And then lastly, we talked about the Earth's internal structure. And there's all these different layers within the Earth, and it's not uniform. We have a variation in these internal structures of being solid, being plastic, or being liquid. And therefore, the Earth's internal structure is not uniform. Okay, that's it for this lecture.